Here's the working model interface. We'll click on New to create a new document, and let's just briefly discuss what we see on the palette here. We have the Shapes palette. We can create these different shapes, for example a curved polygon, and if we double click these bodies after we create them, we can see that they have different conditions we can specify. So we can specify its X and Y position with respect to the global coordinate system. We can specify initial conditions, material type. We could specify friction coefficients, both static and kinetic, and then elastic coefficients. This is also known as the coefficient of restitution that we can use when we define collisions between this and another body. And we also have some static charges that we can, or electrostatic charges that we can use and define the density for it, and some different options here for the moments. So let's go ahead and just close that, and we'll delete this body. And then next we have the join and split, and I'll explain that here in a few minutes when we get into the demonstration. But these right here, these are point elements, a pin, a square point, slots, and what we can do is we can add a point element on one body, for example a point on one and then a slot on another, and then we can use this join tool and it will join the bodies and bring them together and connect them kinematically with the constraint. And so if I use a point and a slot, it's going to create a slot joint automatically. So I can use these point elements. You could consider them children of the main constraints, or we can come on, and if the bodies are already connected to one another, or overlapping one another, for example if we have two members like this, we can just click on the constraint, click over the two, and then maybe anchor this and I'll run it, and we can just simply create a constraint like that. So let's go ahead and remove that. And then down here further we have the mechanical elements, springs and dampers, gears, motors, actuators, separators, rods and ropes and pulleys, and we can customize. We have generic cord-to-cord constraints where we can create, I need objects here to be able to bring it up, but we can create say a pin with friction or a slot with friction, and maybe add a motor or a spring along with it. We can add several things into a constraint using this generic cord-to-cord. So let's go ahead and let's get started with our demonstration, and that is going to be creating a Whitworth mechanism. And basically a Whitworth mechanism has a faster return stroke than it does an advanced stroke. So we'll just create something simple here to get the idea of the ease of use of working model, and then also demonstrate some of the main features in here. So we'll get started by going into our unit settings here, and we can choose from different unit groups. I'll choose SI degrees, and then if I want to customize anything within that group I can click on more choices, and we'll specify maybe millimeters for distance. Choose OK, and then I'll also turn on grid lines for the workspace. We can see that, or XY axes. I can turn on grid lines as well, so if I have the grid snap turned on, I can use the grid in certain grid spacings to create objects. I can also turn on rulers, and we get these rulers on the sides, top and bottom, for the X and Y positions that help us size the parts. We're not going to use those in this demonstration, so I'll turn those off. Now that we have our origin here, just as a reference, that's the reason we turned that on, I'll go ahead and I'll click on the circle tool, and I'll create a simple circle, and then I'll right click on it, choose the geometry, and here I can modify it. I can also parameterize this radius if I want it to be a variable that changes. So for this one I'll just specify 100 millimeters for the radius. It's going to make it quite small. I'll zoom in, but I'll double click that, and I'm going to set this exactly at the origin. Just makes it easier as a starting reference for the model. And once I do that, I'll do a zoom all, and then we have our circle. Next we're going to add a point onto this disk here, and we're going to parameterize the X position of the point. So first let's add the motor onto the disk here so it doesn't move around on me when I'm moving the point. Just click at the center, and if I run the simulation I can see that that motor is attached to the disk, and it's rotating at a constant 1 radian per second by default. We'll go ahead and we'll change that because we're going to change it later anyway. So we'll change this to maybe 360 degrees per second. Now we'll go ahead and we'll add a point element onto the disk. And if I move my cursor around the disk, I have these different snap points that'll wake up. On rectangles, I can use the midpoints and the endpoints and things like that. So here I'll just put it anywhere on the disk because I'm going to specify the coordinate positions for that point. Now, I have the point selected after I placed it there. I can either define the X and Y positions, or I can click on Define, New Control, and I can specify X and Y offset sliders. So these sliders can be used to control this point's position in real time, either before or during a simulation. So pretty powerful capabilities there. We're going to go ahead now. If I double click the point, I can see that because I defined offset controls for this point, it automatically assigned the IDs of these sliders into these fields right here. So for the Y position, I'm not going to vary it. I'm going to leave it at 0. So we'll go ahead and do that right now. Notice how that point dropped down to the Y 0 position. So we're going to just control the X using this input 7. So I'm going to get rid of this Y slider. We don't need that. And then for this slider right here, I can double click it and I can specify a lower and an upper boundary for it. So for example, I could say 10 as the lower value, and let's say maybe 90 as the upper, and then I can specify 80 increments so that when I drag my slider it will snap in 1 millimeter increments. Okay, so now if I come down here to the slider and I move this, you can see the point here on the disk is moving. So that'll come in handy for going through different what-if scenarios in the simulation setup. So let's start next by creating a slider. I'll just click on the rectangle tool. I'll draw some arbitrary rectangle up here. And then I'll go ahead and I'll click on the keyed slot constraint here. And notice how, again, I hover over these. I get these different snap points that wake up. And I can turn that off. I could have arbitrary snap if I wish. I'll click on the bottom corner, good place to put that. And anything you join in Working Model will behave kinematically. So this is similar to what a lot of CAD systems will do nowadays. The difference here is that we're going to be able to calculate all the physics behind what's going on and obtain information such as friction force, velocity, acceleration. So if I click, hold, and drag, I can see that I've got the kinematic control to this, and it has just the 1 degree of freedom there. Okay, so next we'll go ahead and we'll add a slot, or excuse me, we'll add a point element at the center of this slider right here, and we're going to use that point element in just a moment. Next, let's go ahead and create a link. I'll just draw some arbitrary length right there, and then I'm going to click on this slot element and then create a slot going right down the center of that link. So now with that slot selected, I can hold down the Shift key, I can select the point that I created there, and then I can click on Join. This wasn't available just a moment ago, but it is now. So now I've joined those two together. So now if I click on this, drag it around, I can see I have that kinematic relationship there. And it doesn't recognize that there's an end to the slot. I could easily enough do something like add a separator in there to tell it that it stops at a certain position. So let's go ahead now and let's hide this slot because we're going to add another one that will connect it to this point. So let's click on the slot element tool again, hover over the center. Okay, there's our slot. We can hold down the Shift key, click on the point. Notice the join feature woke up again. We can click on join, and now we've got those two slots joined together. Okay. All right, and then let's go ahead and let's maybe drag this down to some position at the 6 o'clock position down here, and we'll just create a pin joint. I'll click on the constraint, hover over the edge of that, and it wakes up. So I've just created a pin. And for the position here, I could also do something like create slider controls that vary the position. So it would allow me to investigate many different scenarios. So we should be set up to run here if we just click the run button. Sure enough, we can see we've got the proper arrangement, and we can adjust the resolution to the animation as well. If we click on World Accuracy, we can change the step size to something like 0.001. This will give us more frames per second, in this case 1,000 frames per second. And then for the integrator error here, let's specify maybe 0.1. For this example, it's pretty much a closed loop form, kinematic form system. It's not going to have a lot of dynamics involved that are going to require a lot of prediction. So we could get away with a larger error in this case. So we'll go ahead and choose OK. Now if we run this again, we've got the same speed on the motor, but now we're capturing more frames per second. So the more frames per second is going to benefit us in two ways. Number one, it's going to give us a better resolution to any AVI file that we might save from this. It'll also give us more data points on any plots we might create. So I'll go ahead and stop that, and if we drag the slider back and forth down in the bottom, we can replay the saved results of the animation. So let's go ahead next and let's start taking a look at some of the visuals that we can put on here for post-processing. So let's take a look at some of that. First, let's create a meter for the velocity of the slider. Right-click on the meter and we'll choose Measure, Velocity, X-Graph. Notice how we have many different characteristics that we can plot for this. Choose X-Graph here, so that creates this meter. First, I can resize these meters if I click on these corners and drag them out. I can also change the display type. So if I wish to view in, this would be a sort of a progress bar form. You'd see a shaded bar moving up and down. Or we can view in digital readout here. Probably expand that a little bit. So we can just toggle between those by clicking on that arrow. Next we can go ahead, maybe let's take a look at the force in this slot right here. So I'll right click on that slot, Measure, create a meter for the force on that joint. And let's go ahead and run the simulation, see what that looks like. Okay, so easy enough to get the data out of here. I can export this data to a spreadsheet if I wish. I'll go ahead and reset that now. Now I can also turn on graphical vectors that are good visual pairs when you have meters on the screen. So for example, if I right click on this body, choose Vectors, Velocity, and I'll do one for this red link here as well. Now if I run the simulation, I get these, I'm going to stop that, I get these vectors showing me what's taking place. So this is very useful. I can do this for things such as the force as well. So if I reset this and create a vector for the total force on that, and then run this. So I have a lot of visual information, so I could create the meters for this as well. So another very useful feature of Working Model is its ability to help you reverse determine, say, the torque required in a motor or the force required in an actuator to actuate or turn something. So in this case, we have a motor rotating this disc, and we have all this resistance on it. Well, we don't have much yet. I mean, this is an ideal system. We don't yet have any friction on these slots or pins or anything like that. But we can certainly add that complexity to the model. And the benefit there is that we can create this torque meter, or a meter for the torque on the motor. And then we can make changes to the model and begin adding that complexity through friction, different resistance and things like that, any load this thing might be moving, and we can study the effect on that. So let's go ahead and just enlarge this meter for the torque a little bit. And now if we run this simulation, this is rotating at a nice constant speed like we specified, 360 degrees per second, but as a result, this is the torque profile file required to achieve that constant velocity. So if we were to export this curve to Excel, for example, and read it back in, we could drive the motor using this data. And then because we'd be driving it with a torque rather than a velocity, you know that other forces can overcome other forces. So if we put a heavy load on this, we're certainly going to affect the ability to maintain that constant speed using this profile. So this is good. We can investigate different things. Let's stop this now and let's click on World, and we'll choose Retain Meter Values. So now we'll go ahead and we'll make a change to the model. So let's reset this, and then I'm going to click on this slot right here, and then I'm going to click on Script, and I'm going to add slot friction. So now I've got a friction assigned to that slot, and it generated this slider for the friction coefficient. And just like the other slider that we created, we can vary the upper and lower bounds for this. So we'll move it to something maybe like 0.15, and then we'll go ahead and run the simulation again. And if you notice on this torque plot, you'll notice the difference now by adding friction into it. Okay, so we could certainly zoom in on this, but I think you get the idea. Now I can change this in real time, and you'll notice the immediate response on our torque plot as a result of that. This concludes the demonstration of building a Whitworth mechanism in Working Model 2D. Please be sure and check out the other half of this video where we'll read in DXF geometry of a cam follower mechanism.